class, we are going to see about the analysis and designs of sequential circuit. So we know already what is a sequential circuit and what is the difference between the combination logic circuit and the sequential logic circuit. Combination logic circuit, it does not have any memory. The output depends on the present input. The output depends on the present input. That's your combination logic circuit. Example, we can say that you have a coffee dispenser machine in a building. Assume that you have a coffee dispenser machine in a campus building. So you have only two states, either 0 or 1. For example, if the coffee is rupees 10, if you are giving rupees 10 into the coffee dispenser machine, it will give the coffee. If the input is less than 10, for example, if you are giving 5 rupees, it won't provide your coffee. It will reject the input and give back your 5 rupees to you. Okay. So you have only two states here for the coffee dispenser machine. The same machine can also be designed by applying a sequential logic circuit. For example, you can even provide 100 rupees, and you can even give 50 rupees, and you even give 30 rupees. So if in all the cases, it will get the rupee and return back the coffee as well as the remaining amount. And if your input is less than rupees 10, it will reject. So these are the possible states of the machine, but all these states are finite states. All the states of the machine is nothing but the finite state. And this coffee dispenser machine can also be designed as a finite state machine, So coming to the analysis and design, for example, again, this instead of a coffee dispenser machine, we have a 64 kilobyte of memory. Okay, assume that each line of memory, assume the memory as a page of a notebook. Each line of memory can store 8 bits. Okay, assume that each line of memory can store 8 bits. If you have 64k number of lines, assume that how many number of bits you can store, how many number of states you have. That sort of memory is nothing but an infinite state machine. Though we can tell it as finite with 64k, but designing this sort of state machine is difficult. Okay, it is difficult. So we need to know how to design these logic devices or digital logic devices with memory, or how to give memory for digital systems. See, for the first case, for a simple coffee dispenser machine with two states, it is a combination logic circuit because it doesn't have a memory. Whereas if I'm applying n number of states, if I'm applying an n number of states, that can be done only if you have a memory. Because with the memory as well as the combination logic circuit, the digital logic circuit will come to a decision that you have to send the remaining amount or you have to reject, and along with the remaining amount you have to send the coffee. Like that, the states will be determined. Okay, the states will be determined. That can be done by using your sequential circuit. So now, so as of now, so the output depends on the sequential circuit is nothing but the output depends on the present input as well as the previous output and keep in mind the you have an output from the sequential circuit only when you have a change with respect to the clock, when you have a change with respect to the clock, and or I can say with respect to the clock transitions only, along with the input you have an output. So this feedback mechanism in electrical engineering, we can say memory as a feedback mechanism in which the output of a combination logic circuit is delayed for some amount of time, and then it is fed back as the input to the circuit, and then it is fed back as the input to the circuit. Okay. So coming to the combination logic circuit and the sequential logic circuit, the main difference is, so for the combination logic circuit, the output for a given set of inputs is independent of the order in which these inputs were changed. For example, I may give any set of inputs. I will have a specified outputs or a stabilized outputs. Okay, after some time I'll be getting a stabilized output. That is your combination logic circuit. But whereas the sequential logic circuit, you have to give the input in sequence. So the order of the input is quite important, because that produce significant differences in the output. That produce the significant differences in the output. That is the main difference between the combination logic circuit and the sequential logic circuit. Coming to the sequential logic circuit, as I discussed earlier in the flip-flop class, we know that Q of T is nothing but the state of any sequential circuit. I'm telling you, sequential circuit is nothing but the digital circuit, where your flip-flop is one of the component of the sequential circuit that is available in the feedback part of the sequential circuit. Okay. So now Q of T for the entire circuit as such, for the entire digital circuit as such, okay, if you have a digital circuit like this, okay, assume this is a sequential circuit, this is a sequential circuit. In the sequential circuit, your flip-flop is one of the part of your sequential circuit, and this is in the feedback path of your sequential circuit. This is in the feedback path of the sequential circuit. So for this circuit as such, you have Q of T for the current clock input, because for the entire sequential circuit, you will be giving clock here. And this clock, if it is common for all the components, and you have a common clock, that is said to be synchronous sequential circuit, because two types of sequential circuits you will be having: synchronous sequential circuit and asynchronous sequential circuit. Synchronous sequential circuit and asynchronous sequential circuit. And now if you have this clock input, and if you have a sequential circuit, you have Q of T is nothing but the state of the sequential circuit at time t, and this is basically its memory. This is basically its memory. What is there available in your, what is the digital data available in the memory? What is the digital data available in the memory? And then the state of the circuit, this state can be changed, okay, from Q of T to Q of T plus 1. Okay, when your clock when there is a clock transition, okay, when there is a clock transition from Q of T to Q of T plus 1, I should not say Q of T, when there is a clock transition from T to T plus 1, I'll be having a state transition also from Q of T to Q of T plus 1. Okay, so the constraint on the synchronous circuit is that the state of the circuit changes after the input. Okay, so only constraint is along with the input, okay, along with the input and the Q of T, you have your output, or your you have a state transition. Okay, along with the input only, you have a corresponding state transition and the output corresponding state transition and the output. See, at Q of T, you will be having an output for the circuit. Okay, and at Q of T plus 1 also, you have an output for the circuit. These with these state transitions, okay, the output, there is an output change only when there is a clock transition change. Okay, and that happens when there is an input change. That happens only when there is an input change. Okay, and coming to the sequence of the synchronous circuit, how it is going to be operated, how your synchronous circuit will be operated. There are, I said already, you have two types of sequential circuit. One is synchronous sequential circuit and another one is asynchronous sequential circuit. Synchronous sequential circuit will be having a common clock, and asynchronous circuit won't be having a common clock, and it is quite difficult to construct, and that we will see it later. Now we will focus on the synchronous circuit. We will focus on the synchronous circuit. So in what sequence your synchronous circuit will be working as? At time t, we have an input x. Okay, for any circuit we have an input. For any sequential circuit we have an input x at time t. Okay, at time t, and the state is said to be Q of T, and keep in mind, this Q of T will be there in the flip flop, where flip flop is one of the component of your sequential circuit. So as a result of the input and the state Q, because this is, as I said, the state Q or the previous output of the sequential circuit, along with the input and your Q of T, a new state is computed, which is nothing but Q of T plus 1. A new state is computed. at time t plus 1, at time t plus 1. And this new state will be available at the output of the sequential circuit only at time t plus 1. Okay, note that q of t plus 1 is not available, okay, to the input of sequential circuit until the next time step. For example, if this is the current state of q of t plus 1 is the current state, this won't be this will be available, this will be available at the input, because this will be stored in the flip flop and then fed back to the sequential circuit along with the input, only if we have the next clock transition, meaning only at q of t plus 2, this q of t plus 1 will be available for the as input to the sequential circuit, as input to the sequential circuit. So there are two approaches to understand the sequential circuit. One is nothing but the analysis of sequential circuit, and number two is nothing but your synthesis, or otherwise said to be the design of sequential circuit. Okay, this is how you can understand your sequential circuit. The first step is your analysis. Analysis is nothing but it begins with the circuit diagram. Assume that the circuit diagram means this sequential circuit, you have this black box. Consider this as a black box. You have a sequential circuit in it. Okay, so it begins with a circuit diagram or a black box, and it ends with an identification of a sequential circuit implemented by the device. Okay, so you have to assume that it's a black box. You have a sequential circuit, and you will be start analyzing the circuit, and finally what what you will be doing, you will be identify what is there in the black box. Okay, so it begins with the sequential diagram and or a black box and ends with the identification of the sequential circuit. Okay, so, and how these steps are carried out is, first identify the input and output for the given sequential circuit. What is the input and what is the output of the sequential circuit, and express each output as a Boolean function of inputs and a present state. Boolean function of inputs and present state, because here in sequential circuit your output depends on the input as well as the present state, that is said to be q of t. Okay, which is otherwise said to be the previous output of the sequential circuit, previous state output of the sequential circuit. And then finally identify, if you could identify the circuit, identify it. Okay, identify the circuit if possible. So how you're going to approach any circuit. Okay, so first I said if your first step is nothing but analysis. Okay, how I identify what is your there as input and output. Okay, identify what is the input and the output and express the Boolean expression. That is step 1. And step 2 is design. What is there in the circuit? Design is about the complete description. Okay, what happens when you give this input and when this previous state is appearing, what will be the output, about the complete description of the circuit. And finally identify what is there inside the black box. What is the circuit, how many number of gates is there, like that. Identify with the possible design inside your sequential circuit. That is your step 2. So coming to your finite state machine, the finite state machine is nothing but you have finite number of states. You have a finite number of states, and finite state machine FSM is said to be finite state machine. It will be having finite number of states. As I discussed earlier, a coffee dispenser machine with a memory. Okay, that will be having n number of states. So finite state machine is associated with memory, and memory has the identifier of the state. Okay, has the identifier of the state. So with the present input and the identifier is nothing but your present state q of t, or the what is the output that has happened in the previous clock transition. That is said to be the identifier with the present state input and q of t as the identifier. The machine moves to the next state. Okay, machine moves to the next state. So, finite state machine is read after the flip flop. Keep in mind, only if you have a memory, you can design a sequential circuit, and only this finite state machine will be having a number of states, and this can be read only after the flip flop. Okay. So, meaning example here is I can take a washing machine. So, washing machine, you have n number of states. Namely, you can have a spin, you have a rinse, and you have a dark wash and a silent wash, and a mixed wash, like that. You have n number of states here, and those states are controlled by a control unit, which is nothing but the knob which is available in your washing machine. Okay, that is an example of a finite state machine. One of the example of a finite state machine. And the state diagram. Okay, this state diagram, what is mean by state diagram of a finite state machine? So if you have finite number of states, as I said, now you have defined states in the washing machine. In the washing machine, you have finite state also. So these finite states can be represented by the state diagram. Can be represented by the state diagram. Consider this state diagram. Consider this as a state diagram. This is nothing but the state diagram of a sequence detector. We are going to discuss. This is an example. So this is an example of a state diagram of a sequence detector. Okay, this is a finite state machine. Okay, so not all the finite state machine have an output associated with the transition uh, with the between the states. Okay, not all the finite state machines. See here, so between the state means this is state A. Okay, from A, B, C, D, E and A. Again, these are different states of the finite state machine. This is a machine, sequential machine or a finite state machine. You have different states, namely A, B, C, D, E and A. Okay, so between states, you are representing 1 and the 0, where 1 is nothing but this 1 and 0. Okay, this 1 is nothing but the input for the circuit, the input for the given circuit. Okay, so input for the given circuit. Assume that this sequence detector is inside a black box. Okay, this sequence detector is inside the black box, and you have an input for the machine. Okay, sequence detector, or this is otherwise said to be the finite state machine, because this is a circuit with finite number of states, and that machine is nothing but a sequence detector. It is a synchronous sequential circuit, and you have an input for the circuit, you have an output for the circuit, you have an output for the circuit. Okay, so the input, let me name it as x. Okay, let me name it as x as the input. Okay, x as the input. So now, mm, yeah. So now, so this is your input, and what will be the output? Okay, what will be the output, and what is the state? Okay, this is representing this 1 0 represents 1 slash 0 represent, this is your input x. Okay, let me assume the output as z. Okay, this is nothing but 0 represents your output of the sequential circuit, output of the sequential circuit with z, with z. So this is x and this is z, and this is nothing but states. From the present state it is going to the next state, from the present state it is going to the next state with an output of 0, having an input of 1. So I can say this is, for example, if this is q of t, this is q of t, and this will be q of t plus 1. Okay. So with the present state and with the input 1, you have an output 0, and the state of the machine is q of t plus 1. Now in the clock, when the clock transition is in t plus 1. Okay, t plus 1. So this is how you will be representing. So not here this particular state machine, if you look here, all the all the states has an output, all the state has an output, the second variable is an output. Okay, the second variable is an output. If you could see, all the state has an output, all the internal states also has an output, but not all the finite state machine will be having the output. That is what here I mean to say. So not all finite state machine have an output associated with the transition between the states, but this particular sequence detector does it. And all typical of finite state machine represent synchronous machine. So transition between states and production of output. Okay, transition between state in the sense here A to B between states, and production of output in the sense from A to B your output is 0 for this case considered. and takes place at a fixed phase of the clock, depending upon the flip flop used to implement the circuit, because you have four different types of flip flop, and we don't know what flip flop we are going to use and what is the output of that particular flip flop, because that is well defined by in the previous class, and what is your present state and the input, what will be the next state and the output of the flip flop. Based on the flip flop that we are using it in the sequential circuit, your output of the circuit will also change with respect to the clock. Okay. Similarly, not all finite state machines will be having this sort of complex diagram, because you here in state A itself, from A state A to B, I have input 1 when I want to, when my input is 1 and when in my state is A, okay, the output is 0. I'm telling like that. And when the present state is A, okay, when the present state is A, and when my input is 0, my output is 0. Okay, my output is 0. Okay, like this is a complex diagram. Let us identify this or analysis can be done by this complex diagram itself. Yeah. So now first thing is you need to represent the given state diagram. You need to represent the given state diagram with your state table. Okay, with the state table. So now tabular representation. This is your state diagram. This is your state diagram that is represented by ST. So represent the state diagram in a table. That is said to be state table. Okay, that is said to be state table. So here, see here, Q of t is said to be the present state. Okay, Q of t is said to be the present state. Q of t plus 1 is said to be the next state. Okay, Q of t plus 1 is said to be the next state. Along with the output, you are going to represent in the table. So now, what are the possible state in the state diagram? A, B, C, D and E. So A, B, C, D and E. Okay. So when your present state is A, when the present state is A, and when your input is 0, okay, when your input is 0, when your input is 0, when your present state is A, and when your input is 0, we have two inputs. See here, when your input is 0 and input is 1, keep in mind you have input slash output between the transitions. You have input and output in the transitions. See, these are nothing but your it is a sort of discrete mathematics where you have a directed graph. This is your directed graph with loops also, and it is not a simple graph. It is not a simple graph. You have an arc. You have an simple graph. You don't have an arc connected with its own vertex. But here you have an arc connected with an own vertex. Okay, own vertex. So labeling between your directed graph, labeling on the arc, it is nothing but x bar z, which is nothing but x bar z. The labeling, which where x is nothing but your input and z is nothing but your output. Okay, x is nothing but your binary input and z is nothing but your binary output. Okay. So now this is a finite state machine. We are going to read how your finite state machine reacts with respect to the input, and reacts to input and makes a move between the state, reacts to the input and makes a move between the state and produces an output, This is what we are going to focus here. So now I said you have five different states for this particular state diagram. So A, B, C, D and E. A, B, C, D and E with A slash 0 means, so here particular state from A to B. Okay, if your present state is A, if the present state is A, I have two inputs 1 and 0. I have two inputs 0 and 1 or 1 and 0 either way. So input x is equal to 0, input x is equal to 1. Input x is equal to 0, input x is equal to 1. So when input x is equal to 0, okay, what is my output? My output is 0. My output is 0. Okay, input x is, because I am writing what is this next state as well as this is my next state. Q of t plus 1 is next state. What is the next state as well as the output? Okay. So when my input is 0, present state is A. When my input is 0, okay, my output is 0. And what is the next state? Next state is also A. So A is the next state and output is 0. And next one, when my present state is A, when my input is 1, okay, input is 1, and what is the output? Output is 0. Output is 0. Okay, the output is 0. Here I have represented. Output is 0. And what is the next state? Here it is going to the next state. It is B. B is the next state. B is the next state. I repeat for one more. So my present state is B now. My present state is B now. Okay. When my input is 1, I have only one combination here. One combination here, that is moving between the next present state and the next state. So now here see, B input can takes again X, input is X for us. X take the value of 0 and 1. X takes the value of 0 and 1. When X is equal to 0, when X is equal to 0, when X is equal to 0, what is my output? Output is 0. And what state it goes to? A. So output is 0 and it goes to state A. So when input is 1, my output is 0 and it goes to the next state C. So output is 0 and it goes to the next state C. So like that, each and every step, for each and every step of, or for each and every present state, and along with the inputs, derive your next state and the output. Okay, this is your state table. This is your state table. And next we will go ahead with the transition table or output table. Transition table is nothing. This is the transition table or output table, and it's another tool in the design and analysis of sequential circuit. Is nothing but your transition table. Okay, this transition table is another tool for analysis and design of a sequential circuit. Okay. So what is the difference between your previous state table and this transition table is, here you have represented the states as alphabets A, B, C. Instead, I am going to give certain binary numbers for each state, and I am going to replicate the same table with the binary number. So that is the transition table. See here, the same, this is the state table. So A, B, C, D, E, these states are given or assigned an equivalent binary numbers. So I am giving A as 000 and B as 001, C as 010 and D as 011. E is equal to 100. E is nothing but 100. So likewise, the state table, I am converting it into transition table. Okay, I am converting it into transition table by assigning the binary numbers to each states. Okay, so the transition table is nothing but you will be having binary values. You will be having only binary values for the present state and the next state and the output. That is your transition table. So, and convert now again the transition table as a truth table. So what is a truth table? Truth table is nothing but generally what we know about truth table is you have an input and you have an output. For this set of input, what will be the output? And since this is a sequential circuit, along with the input and the present state, you will represent the output. Okay, and the next state, you will be representing the next state and the output otherwise. Okay. So now these binary digits, I have assumed the 000 for A and B 001 and C it is 010. Likewise, I am assuming this states. I am assuming the states. So from this states, okay, from this states, what am I going to do is I'm assigning equivalent variable for this states. Three variables we need in terms of y as y2, y1 and y0. So y2, y1 and y0 are the binary states, and for x is equal to 0 input and x is equal to 1 input, and what is my output and what is the state? What is the state? State is represented by a 3 binary bits. So y2, y1, 0, y0, y2, y1, y0. I'm separating it and writing, that's it. Okay, not much of difference. I have separated this and I'm writing. I'm using two columns, 000 as one column and 0 as the output for separate column, because that is the truth table, right? With respect to the input and the present state, what is my next state and the output? So this is the modified truth table. I'm instead of writing x is equal to 0 and x is equal to 1, let me write it here itself for 0 0 0 for input for the input 0, and if the present state is 0 0 0, what is my output and the next state, like that. See here, modified truth table as an extension. See y2, y1, y0, 0 0 0. I'm taking input here itself. Instead of two separate columns, I'm using in the same column x is equal to 0, x is equal to 1, x is equal to 0, x is equal to 1. Like that for each different states. So for 0 0 0, what is my, when my input is 0, what is my next state, one my output. Okay, this is how I can modify my truth table. See here, the previous case, when my present state is 0 0 0, when my input is 0, my next state is also 0 0 0 and output is 0. So when this is 0 and my input is 0, next state is also 0 0 0 and my output is 0. And when my present state is 0 0 0, when my input is 1, the next state is 0 0 1 and the output is 0. So when my present is 0 0 0, when my input is 1, the next state is 0 0 1 and my output is 0. This is how I'll be modifying all the 1, 2, 3, 4, 5 combinations plus 5 combinations, 10 combinations of output. Okay, 10 combinations of output for the present input and the present states. Okay. So how to represent a finite state machine? There are three representation of a finite state machine. There are three representation of a finite state machine. So first one is state diagram, the state diagram. The next one is state table, and finally the transition table or the output table. So in this class, I have discussed from the state diagram, how to form the state table and how to form the transition table or output table, and finally the truth table, from the given state diagram, how to get the state table and the state transition or the output table, or finally a modified truth table. Okay, this is what we have discussed in the class. And in the next class, we will discuss how to analyze a given circuit, how to analyze a given sequential circuit. Thank you.